Hello and welcome to this session on information retrieval. Today our focus is relevance feedback. So we have already seen how to model queries and documents on the vector space, and today the central question that we would like to deal with is how to improve the relevance that we have got by modeling them on the vector space. So let me remind you, what we do is we take the sentences, we place them on a vector space. To do that, we identify the dimensions and then we find cosine similarity, right? So once we have identified the relevance, we simply return the scores of relevance and we use that for ranking. So now the question is, can we improve those scores by using some kind of feedback information? By feedback, I refer to the information on whether the returned documents were relevant or not. So if this information is available in terms of some kind of feedback, can I use that to improve relevance? Uh, so one way to incorporate the feedback is to do query expansion. So I can now reformulate the query either by expanding or shortening the query and refiring the query onto our index. So here is an example. We call this the problem of synonymy. What result do you expect for a query plane? Usually, plane refers to a flight or an aeroplane as we call it. So let's say if I show you the query plane from Delhi to Goa. Now here the context makes it clear that I'm talking about a plane which is a flying object. But a plane need not always be a flight or a aeroplane. It could also refer to the plane as in the object of geometry. There are many synonyms even within the context of plane from Delhi to Goa, which will work for the web search equally. For example, flight, aircraft, airplane, aeroplane, by air, fly, flight, aircraft, and so on. So some of these are spelling corrections, some of these are synonyms. But the point is, if any of these queries come, we want to give the same result as output. Now, how can I do that? To ensure good results, we usually do automatic query refinement. So the moment I get a query, I'm going to do some processing on the query. Let's call it query refinement. And there are two options ahead of me here. The first option is to use the query or the results for reformulating the query itself. So I take the query information and I take the results. I match them with my index. I take the results and I use both query and results to do the reformulation. So this kind of refinement is called local query refinement. Uh, from this end, we will study relevance feedback, pseudo relevance, and indirect relevance feedback. At the same time, we could do global query refinement as well, where we do not use the query or the results for reformulating the query. So what do we do then? If we are not going to use the information within the query, then we are going to use some global information about the knowledge of, let's say, English, if the query is in English or the language in which the query is. Now, to do that, we could use thesaurus or do spelling correction algorithms. So these are largely query and user independent, whereas these are dependent on query and the user. So here is the context. I repeat, we have a user who has an information need and who is interested in looking at relevant results. So he files a query to a search system and our search system returns some results. Instead of showing these results directly to the user, or sometimes we do show these results directly to the user and then we use the information we get after showing the results to the user. So let's say the user gives us the judgment that results 1 and result 2 are relevant, but the result 3, the document at rank 3 is not relevant. If this information is obtained back from the user, then I take that information and pass it through my search system once again, reformulate the query and try to get better ranking. We can often get this information of relevance from the click information that the user does. So for example, let's say there is a search page in which the user scrolls and clicks on the third link. So this is usually a good clue that the first and the second document were not what he was looking for. The document that he wanted appeared at the third place. Now, these kind of clues can be incorporated or used to refine the results for future queries from either the same user or from a different user. Way back, RefMed system used this kind of query feedback system where along with the search results, they also gave a graded relevance button where they said that okay, something is relevant and something is not relevant and something is neutral. So they ask the users to click on these radio buttons so that the system would know whether something is relevant or not, and then can use this information further to reformulate the query. But guess what? Users don't like to do this. They are always in a hurry, and they just want to look at the results and move on. So in the present day, if we change Google or Bing to this to carry this kind of feedback information, I doubt if users would like it. But in an experimental setting, they should work though. Um, so there are some assumptions we make. So the indexed content is unknown to the user. So the user doesn't know how many relevant documents exist, and so he only knows from the results that the retrieval system has retrieved which of them are relevant and not. And even there, we assume that he doesn't go too deep into the results, as in beyond the 10th page of results, let's say. Um, and information need changes after looking at the results. This is a very common trait or characteristic, you could say. Um, so here's an example. Let's say we visit YouTube to listen to some specific set of songs, but after we issue a query and we see the results, the first result may be too appealing, and we may just change our mind, and we might or it might remind us of another song. After looking at the results, we might have got reminded of some other song that um, we don't care about the current results, even if they were relevant to what I had queried for, and I start reformulating my query and may go for another song. So these things are pretty common in the search world. That's why it's very difficult to read the user's mind and give what he really wants. So understanding the information need is a very big challenge by itself. But we continue with our assumption that the query terms explain relevancy, and we also continue with our intuitions and hypothesis around the term frequency and its connection to relevance. Here is a recap of vector space models to you. Remember, we have sentences which we are interested in putting in a vector space. So we define orthogonal dimensions, which are made up of those words that are distinct uh, in my corpus. And then I use the term frequency information in each document to define the vector. So if doc1 contains one occurrence of system, one occurrence of retrieval, and one occurrence of information, doc1 would be 1 comma 1 comma 1 vector. So likewise, I could make the documents and put them on the vector space. I could make these vectors unit vectors at the time of preparing this index, so matching is faster. And then I compute similarity between two vectors. So let's say there's a query vector and there are several document vectors. The similarity between document and the query vectors is simply the cos theta between them, cos of theta between them, or in other words, it's simply the normalized version of A dot B. All right, let's now discuss the meat of today's talk, which is how to get the relevance feedback information and incorporate it so that we can reformulate the query and we get the right kind of reformulated query which matches more relevant documents. So this idea is due to Rocchio. The Rocchio algorithm for relevance feedbacks central idea is pretty simple and pretty neat. So let's assume I have a vector space. So I simply have given a two-dimensional projection of my vector space here. Assume you have lots of relevant and non-relevant documents. Here X marks non-relevant documents and zeros or O's mark non-relevant documents. All right. So let's assume this is how my space is. Then what do I do? And let's assume this red triangle marks my initial query. So initial query is here. And if this initial query forms the centroid and I am interested in the angle between the vector connecting this to the origin to all the other relevant vectors, right? So you could imagine that the query acts like a centroid and the nearest documents are returned. Now when I make a circle here, I would get some relevant documents and some non-relevant documents. For example, this X, even though it is non-relevant, is very close to the query. And as much as this O, which is a relevant document. I like that I have matched a relevant document, but I don't like that I have also matched a non-relevant document. Now what do I do? So the idea is to move this query vector such that I start matching more relevant documents and less non-relevant documents. So the next natural question is, how do I move the query vector? The idea again is pretty simple. All we do is take the initial query vector q naught and move it towards relevant documents. So let's assume dr, the big D sub r, refers to the collection of documents that are relevant. And let's say I have another big D sub nr, which refer to all those documents which are not relevant, in which case I add the scores of I add the coordinates of the documents that are relevant and I subtract from my initial query vector those documents that are not relevant. So that's the key idea behind this formulation. So what are we saying here? So this essentially translates to adding uh, some kind of weighted terms to my query vector and removing some weighted terms or removing some weight from the terms of my non-relevant documents, right? So if the initial query vector q naught has certain terms with certain weights, then what we are trying to do is include terms with weights from the relevant category and remove or reduce some terms and some weights from the non-relevant category. So that's what the pluses and the minuses are doing here. We use alpha, beta, and gamma as constants to help us scale sufficiently so that we have a QM which now acts as a new centroid, so that I can cover maximum amount of relevant vectors. Let's look at this with an example. Let's assume I have an initial query: cheap CDs, cheap DVDs, extremely cheap CDs. And let's assume D1 is CDs, cheap software, cheap CDs. And let's assume D1 is judged as relevant. Let's also have a D2, which is cheap thrills DVDs, and let this be non-relevant. Now, if I apply Rocchio on this, what would the revised query vector be like? Let's solve this together. And we are going to assume a few things here. Usually alpha, beta, and gamma are empirical constants, but in this case, we'll go with alpha equals 1, beta equals 0.75, and gamma equals 0.25, and we'll assume that this is given to us. And I'm not going to do length normalization of vectors, but I assume you know how to do that by yourself. Okay, so let's do the first step first. We take the initial query, which is cheap CDs, cheap DVDs, extremely cheap CDs, and put them on the vector space. So I need 6 dimensions: cheap CDs, DVDs, extremely software. Well, why software and thrills are here? Because they come from document 2. So I have the initial query vector which contains the first 4 terms and zeros for software and thrills. The next objective ahead of me is to compute D1 and D2. You should pause the video here and fill this yourself. When you are done, press the unpause button. Let's look at this. So we have D1 and we have D2. So D2 is cheap thrills DVDs, cheap DVDs thrills. Yeah, so we have cheap thrills DVDs. All right, so we have the vectors ready, and we are now interested in moving the query vector so that it matches the relevant document. Recall that D1 is the relevant document and D2 is irrelevant. It is given to us here. So D1 is judged as relevant. So this information is given to you. So once again, let me reinforce the central idea. We are trying to move the query vector closer to the relevant vectors. Now, how do I move a vector? Here is an example. So let's say I want to move 2, 2 to 5, 2. So if I want to move 2, 2 to 5, 2, I should add 3 to the x-axis, right? So the more I add to the x-axis, I keep going towards the new vector, right? So that's, so if you take the difference between 2 and 5 and 2 and 2, the independent components of these vectors, then if you try to bridge this gap, you tend to move towards the other vector, right? So that's the intuition. So we want to take, since these numbers represent term frequency for us on specific dimensions, so we want to see where the most relevant documents are, and we want to go towards those documents, or in other words, we want to change the term frequency information of our query, and that we could do by adding or removing some terms to the query. So basically, if I know the universe of known and not relevant, relevant and not relevant documents, I can then take the query and add or remove some words to that query so that I can now move towards a better match. So that's the whole idea. So that means I am interested in D1's words, and I am interested in adding some of them to DQ0, and I'm interested in removing some of the terms from D2 from Q0. And this is the Rocchio's algorithm formulation. So let's try to apply that here. Remember, the number of relevant documents is 1 in our example, and number of non-relevant documents is also 1. So these two terms disappear. Alpha, beta, and gamma are constants which we have assumed to be 1.75 and 0.25. So that also simplifies stuff. And summation is acting over only one document, so the summation also go away in this example. So all I have to do is simply Q0 plus 0.75 D1 minus 0.25 D2, and that's all I need to do. So I have Q0, and I need to add 0.75 times D1 to it and remove 0.25 times D2 from it. And if I do that, I get 4.25 for the first dimension. I do this similarly for all the vectors. So this is, remember, this is vector addition and subtraction. So once I have done that, I get a a resulting query vector. In this case, notice that this should give you a negative value. Q0 is 0, plus 0.75 times D1 would also be 0. Minus 0.25 times D2 should give me minus 0.025. But since we can't have minus 0.25 times a term thrills occurring in a query, we simply make it 0. So that's all we have here, and now I have a reformulated query, and if I issue this query, I'm more likely to match the relevant documents, or I'm closer to the relevant documents and I'm farther from the non-relevant documents. So this was the idea behind Rocchio relevance feedback. What do we do if we don't have user judgments at all? So we call this a blind relevance feedback or the pseudo relevance feedback, where we assume that the top k ranked documents are relevant. So in this case we are trusting the search engine. So we ask the search engine to do the regular matching, the normal way it does matching, let's say cosine similarity, and it comes back with, let's say, some 150 hits. Now out of the 150 hits or 150 matching documents, we say that let's say the top 10 are relevant always. If that is the case, we just assume that the top 10 are always relevant, and we try to incorporate a relevance feedback system which leverages the words in the top k documents. This need not be always a good idea, because this has a major problem of query drift. Let me explain what a query drift is. Let's say the query was on cricket, uh, and specifically, let's say Dhoni retires from first class cricket. Let's assume the user's information need is to read more about Dhoni's retirement from first class cricket. So he's used a query: Dhoni retires from first class cricket, and uh, we get several documents, and let's assume the top 10 documents were indeed relevant to this query, and let's assume the first hit talks about Dhoni's retirement, and somewhere in there the document used a very rare term, let's say uh, Chile or Africa, and it said that Dhoni had even gone to these countries or continents, and he has played cricket there somewhere while explaining his retirement and his professional career. Now that we want to move towards these documents, what we do is we try to get these weights and we try to incorporate them as we move closer to the relevant documents. So what we do is we take Chile and Africa and assume that these are relevant terms which I should add to my query. So while I go closer to this to these 10 documents, now you can expect that we are going to match more documents which are related to Chile and Africa. So let's say there are a few articles which talk about Dhoni playing in Chile and Dhoni playing in Africa. Now I start matching them instead of some of the other documents I would have matched in the earlier case. And if I keep applying this iteratively multiple times, I tend to go more and more closer towards Chile and Africa. And this is what we call as query drift. At some point of time, I start showing results about Chile and Africa and not about Dhoni at all. And that's not welcome. There is also indirect or implicit relevance feedback, where we don't ask for judgments from users. We also don't take the top K documents as relevant. But then, how to incorporate relevance feedback? Well, in this case, we use data logs like click streams that we have. So when users click the results, we know which result he clicked. We ideally want the user to click on the first result that I return. But if the user is not doing that, then I know that the first n minus 1 results, where the nth result is where he clicked, are not relevant, and I want to go away from those results, and I want to go towards results which are similar to the nth result. For this, I could use clickstream mining. So clickstream mining also tells me what is the right relevant answer for a given query, right? So for this query, this seems to be a relevant answer. So this kind of judgments can be extracted from clickstreams. So let's recap. We are talking about automatic query refinement, and query refinement can be local or global depending on whether they are user and query dependent or not. On the local query refinement side, we talked about the relevance feedback algorithm from Rocchio, where we move the query vector towards relevant documents. We talked about this formulation of the relevance algorithm, and we worked out an example. I also told you that sometimes we go for top K assumption that the top K documents are relevant. And this kind of relevance feedback is called pseudo relevance feedback or blind relevance feedback. We could also do indirect or implicit relevance feedback. That is, we use the click streams, query logs, etc. to understand the relevance information. So that was about the local query refinement on how we handle them. Now let's move on to the global automatic query refinement. So remember, these are user or result independent query refinement. So how do we refine the queries without looking at the results or asking the users for judgment? So usually the global knowledge about the language with which the user queries is good enough to do some kind of query refinements. We have already seen spelling correction or using the thesaurus to update the queries or add more terms to the queries is a good idea, and that often improves precision and recall. um, Here is an example of automatic but then we also know that many of the terms in the thesaurus, in the usual language English thesaurus, let's say, is not good enough for my web search kind of scenario. uh, that's because the vocabulary in our search universe is way too huge compared to the vocabulary of a language thesaurus. So I'm forced to generate or create thesaurus in an automated fashion. There are many terms like fast and rapid, tall and height, sound and noise, restaurant and hotel and motel. So many of these belong to equivalent classes when it comes to web search, but need not be equivalent the uh, in the linguistic world. So one natural question is there a way to generate these kind of thesaurus in an automated way? And if yes, how? And there are many domain specific phrases. Let's say you belong to the finance world, or let's say you belong to the sports world. You might have some lingo which might not appear in the thesaurus, the slang words, and so on. There are many that we could go on, which go beyond the limits of thesaurus. So the central question now is how to automate the thesaurus generation. Interestingly, we use an analysis called co-occurrence analysis. The idea is that if two similar documents carry terms, then those terms are similar as well. So here are two essays that people wrote on the same topic, mainframes. Mainframes are primarily referred to mainframes usually are referred usually refer those computers with fast, with rapid. So if you look at it, I can replace some words here and write another essay which means the same thing. So if we have similar such documents, we can extract the terms from these and call them as being belonging to the equivalence class. So that could be one way to prepare the thesaurus. So let's see how to leverage this idea. So a co-occurrence analysis builds a term document matrix once again. So it fills that with how often does the individual terms appear in the document or the term frequency information. So let's say I have book 1, book 2, book 3 and book 4, and book 1 had 400 occurrences of cricket, 5 occurrences of football, 9 occurrences of hockey, and 2 occurrences of tennis. So if I give you a term document matrix like this, can you tell me which books sound or look similar to you? Yes, you're right. Book 1 and book 3 look more or less similar because they have very similar distribution of the terms. So both of them seem to be talking about cricket, whereas book 2 and book 4 seem to be talking about hockey. So most likely, it's very likely that it's a hockey book. So we would like to now do some kind of co-occurrence analysis to pick words related to cricket or pick synonyms from book 1 and book 3. So here are some terms which might not be in my dictionary, but because of my sports knowledge, I know that In cricket, we call a four as a boundary. And in the entertainment world, a movie is a film. But how do I know? Because I did some kind of co-occurrence analysis. Let's just look at these terms in some books, and let's say this is how the frequency information is distributed, right? So if we take the cricket books, they are most likely to talk about boundary and force, and very less likely that they would talk about movie and film. Remember that these terms need not be zero though. Yeah, so they might still occur. They might talk about an odd movie which Dhoni wanted to see, or the movie in which Dhoni featured. There could be some movie information in books related to cricket as well, but it's very likely that you will see boundary and four many more times. Okay, so let's do some magic with matrices now. um, so let's say I have a matrix A. Then what would A transpose look like? So here is A transpose for you. Okay, so let's assume I have a term document matrix T and D here. So that's so I have the terms on the vertical axis and the documents on the horizontal axis. So if that is the case, I have a matrix like this. Can you guess what A transpose would do in this case? Yes, that's right. So we have a term-term co-occurrence matrix as a result if I multiply term document matrix with its transpose. And this is pretty useful for me. So here is another realistic example. So I have a term document matrix. I take its transpose and I multiply it. And what I get is a term-term co-occurrence matrix. If I examine some row of this term-term co-occurrence matrix, I can say that term 6 is more relevant to term 1. So it looks like term 1 and term 6 are synonyms. They appear in similar documents. So that's the core idea behind thesaurus. So there's one idea, I should say, behind thesaurus generation. And if we have such thesauruses or thesauri, I could go ahead and do global query refinement. So let me once again recap. We have discussed query refinement. We have discussed two kinds of query refinement, local and global. So under local query refinement, we discussed Rocchio feedback algorithm, and we also discussed relevance feedback, and we discussed using click streams and query logs for query refinement. On the global side, we looked at spelling correction and using thesauri. From on the topic of thesaurus, the natural question is how to generate automatically a thesaurus from the data that we have. So by looking at the documents, we could generate using co-occurrence analysis, and I showed you a simple technique to do co-occurrence analysis, which works by multiplying a matrix with its transpose. That's all there is for today. See you again for another class on information retrieval. Thank you.